Continuing with the fresh concrete in this lecture, today we shall look into role of mix parameters. What are the mix parameters? First is the paste and water. Then next we will look into role of aggregates, and in aggregates we have grading. We will also look into effect of maximum size of aggregate and their shapes. Also we will look into how to increase workability, how one goes for increasing workability. So, this will be the general outline. So, let us start with role of paste. When we add water to the cement, it becomes plastic. Otherwise, cement is a solid, it is in dry condition, it is not moldable, it will not deform under load just like that. So, to make it plastic, what we do? We add water, and as progressively we go on adding water. Originally dry cement particles are air filled. The voids or interstitial void space between the cement particles will be filled with air, and this air filled now spaces are now gets filled by water, and as they get filled by water, gradually a stage comes. Initially all the surfaces of the cement particles will be dry. As you add water, some surfaces will tend to become wet. Air of course initially forms a kind of open continuous channel or connected air filled system. As you add water, this connection gets disrupted because water fills up and air filled voids tends to become isolated, and a stage comes when all the when all the open air voids are isolated by water and they become air bubbles. This water corresponding to and the corresponding consistency is something close to normal consistency. So, normal consistency we have defined in case of cements, and this corresponds to the state where water is just sufficient to isolate the air bubbles. In fact, it is not totally air free. The voids will still contain air bubbles and they will be isolated. They are independent closed pores where air bubbles are filled, and the ratio of air to water at this stage is about 1:7, and this is called basic water or the water corresponding to normal consistency. Water corresponds to normal, this corresponds to the normal consistency that has been defined, right. Now, if you add more water to it, it makes the paste softer, it makes the paste softer rapidly, and generally dispersion of the cement particle takes place. So, that is the mechanism when you add water to the cement and progressively go on increasing the water content, right. Now, let us see what happens to the rheology of fresh concrete. We have discussed earlier that rheological parameters are the yield shear stress and the viscosity. So, you can look into the viscosity. Nu is the viscosity, delta is a parameter which defines particle dispersion, right. Okay. It defines parameter representing particle dispersion, as we can see now. Delta is a parameter representing distance between particle. So, as I add water, distance between particle will go on increasing, and as this delta increases from this equation, this is viscosity. You can see that as delta increases, viscosity will reduce because delta to the power minus 0.6. So, if I increase delta, nu will reduce, and it reduces till possibly a distance between the cement particles becomes 5 micron. Any distance beyond this, any addition of water and further dispersion beyond this of course, does not cause further change in the viscosity. So, you can see that viscosity reduces, therefore, flow will increase, flow will improve. This is of course nu in centipoids, nu the viscosity in centipoid, and this comes here in one of those equations. Nu 0 is the viscosity of water. Similarly, so you can see that this nu increases with decreases with water cement ratio. As I increase the water cement ratio, this is exponentially related to nu. Higher the water cement ratio, since it is e to the power b, b is an empirical constant into W by C. So, if I go on increasing W by C, nu will reduce, right, and exponentially it will reduce exponentially. So, higher water to cement ratio in case of paste causes better dispersion, more dispersion, and also it causes reduction in the viscosity. So, water cement ratio is a factor in case of paste which causes reduction in viscosity, therefore, improves the flowability. This is even from common sense, this is understandable. The other important factor is the surface area. Other important factor is the surface area of the surface area or particle size distribution of the cement particle. S stands for Blaine's fineness. If you can see that S stands for Blaine's fineness, which means it is the specific surface we define in terms of earlier we discussed in connection with cement. This is centimeter square per gram, it is the specific surface. So, as the specific surface increases, that means the fineness of the cement increases. Specific surface is what? It is the surface area per unit mass. So, if the surface area per unit mass increases, that means it is finer. Finer particle have more surface area compared to coarser particle. So, as the surface area increases, the finer particle sizes are finer and finer, then viscosity will have a tendency to increase, the viscosity will increase, So, this increases, viscosity increases, and this has got some relationship with the water cement ratio also. This is the water cement ratio for normal consistency. If you have more water cement ratio than normal consistency, you can see that the viscosity will reduce. So, this is a more generalized equation relating both water cement ratio and the fineness of the cement. So, higher the water cement ratio with reference to the normal consistency, because if you have normal consistency water, this would be very this term would be 0, this term would be 0, and this is actually very large. So, therefore, viscosity reduces as I increase the water cement ratio beyond the normal consistency, and it increases with fineness of the cement. So, it increases with fineness of the cement and reduces with increase in water. So, flowability will be better for higher water cement ratio and also for coarser cement grains. Finer cement grains will require more water to be plastic, actually, that is the idea. So, that is what it is, alright. So, this factors actually governs the rheology of fresh paste. So, water cement ratio is the main aspect, and of course, the fineness of the cement plays a role in the flowability of the cement paste. Paste itself must be flowable, because if you see all other materials are coarse aggregate and the fine aggregate, they are dry material, and on their own they won't have much mobility. It is the paste which should be there. So, what does actually paste do? If you see the role of the paste, in case of concrete, paste, of course, it will have a little bit of air in it, forms a matrix. I may call it as a matrix in which the coarse or fine aggregates are the inclusion. So, this forms a matrix where aggregates are dispersed, they are the inclusion and they are dispersed. The matrix separates the aggregates and also holds them together. So, the aggregates are separated from one another by this paste which is inside in between, and it holds them together also, it binds them together, even in fresh state it holds them together and acts as a lubricating material, enabling plastic deformation. So, therefore, paste is the main, is the most important part as far as workability or deformability and mobility of concrete is concerned. Paste is the most important part. It is the one which holds the aggregate together, it disperses them together and then gives you a lubricating material enabling plastic deformation. This degree of dispersion of course is not very large, never more than 3 to 10%. That means the volume, if I find out the distance between aggregates before paste was added and after paste was added, this increase in the distance from original distance, mean distance to the increased distance is not more than 3 to 10%. So, dispersion is not more than 3 to 10% and therefore, this is important, but the paste, it is important to have paste and sufficient paste so that it can take care of the dispersion also, right. So, if we decrease the volume of matrix, that is the paste, dispersion, it reduces the dispersion and it will increase the particle interference. It will increase the particle interference resulting in stiffening of the concrete, So, matrix must be sufficient, that is what we understand, that matrix must be sufficient and sufficient to hold the aggregates together and also ensure dispersion of these aggregates together. Now, matrix itself must be capable of flowing itself, it should have low viscosity so that it can move. So, that is the first fundamental. Matrix must be of low viscosity, it should be able to move itself, deform itself, should be capable of plastic deformation, and for that you need a water cement ratio more than the consistency situation, and it should be sufficient to hold the aggregates and also cause their dispersion, so that there is an ability for the concrete to undergo plastic deformation. So, that is the role of the paste, right. Continuing with the role of the paste, if we lower below a level the paste content, if we lower the paste content below a level, right, if we lower the volume of the matrix, it results in harsh and segregating concrete, because if you have too much of, if you have low paste, the aggregates will be left alone, they will not be held together. So, they can segregate very easily. So, and that is the point actually, that is the point. Okay. So, this is the next stage. Okay. Increasing matrix volume on the other hand of course improved concrete consistency, and matrix itself must be, that is what I have been mentioning, that if you increase the matrix volume, it will improve the matrix consistency, I mean the concrete consistency or workability, but and at the same time matrix itself must be adequately consistent. Low water cement ratio matrix may cause dispersion, but cannot hold the aggregate together. So, if you have low water cement ratio, water to cement ratio, that means the matrix is dry, it may cause dispersion. If you put sufficient quantity, it will push the aggregates apart, but will not hold the aggregate together, because it itself is also dry and therefore, it will stiffen. Too high water cement ratio on the other hand, the matrix becomes too thin, it is flowing very thin and not viscous enough to hold, the segregation is there. So, there will be segregation and could be form of bleeding, and low dispersion is and low holding capacity. So, it cannot hold and therefore, there is a possibility of dispersion. So, low water cement ratio is a problem, high water cement ratio, very high water cement ratio is also a problem. Right. Continuing with the role of paste, incidentally normal consistency corresponds to around water cement to ratio of 26 to 0.26 to 0.33, and in our normal strength concrete, as sometime we might have defined characteristic strength of concrete, structural grade of concrete starting from 20 MPa or M20 to about M40 or say M50 or so on, the water cement ratio is usually more than this 0.26, usually it is more than this value. So, normal concrete, normal strength concrete, not very high strength concrete, we are talking of normal strength concrete, the water cement ratio is usually higher than this value, higher than this value, higher than this value. So, this is generally you will have adequate consistency. Well, paste content should be adequate. This is clear that paste content shall be adequate. This should be adequate paste content, that means matrix must be sufficient. Now, we have understood. So, it should be sufficient to fill in all the voids in the aggregate system, but also more than that for proper dispersion. So, it should be more than what is required to fill in the dry volume, interstitial space between aggregate when they are compacted alone. So, it is the amount of paste required is more than that is required to fill the interstitial space of the aggregate when they are compacted alone. So, you need more, because there will be dispersion as you introduce paste into the concrete, so they will cause dispersion of the aggregate particle, and therefore, you need more, right, you need more. But for reasons of economy and of course, factors like shrinkage etc., we can't have too much of paste content. To have high paste content is good, because it will give me workable system, but we can't have too much of paste, because cement is the costliest material in normal strength concrete compared to, let us say, aggregate, coarse aggregate as well as fine aggregate and water. So, therefore, if you use more paste, more cement will be going into it. For a given water cement ratio, more cement will go to it, and therefore, it will be costly. So, I really cannot increase the paste content in normal strength concrete very high. I have to control it. So, therefore, from point of economy, and also it can cause shrinkage and other secondary effects. So, therefore, we do not want too much of paste in the or cement in the system, and therefore, normal concrete the paste content ranges from 28 to 32%. Higher paste content will improve the workability, but we will not do that, because as I said, the economy will forbid us doing that. But in certain special concrete you still do, for example, very high strength matrices, very high strength matrices, not of 20, 30, order of 800 or 250, more than 200, the reactive powder concrete, there the paste content of course is relatively much higher, but that is a separate issue. Also, in self compacting concrete, the paste content is much higher, where I need a lot of flow, but then paste does not consist of cement alone, it consists of cement and others cementitious material. So, therefore, both economy and other secondary effects all are taken care of when we use high amount of paste content. But in normal concrete, what we are discussing at the moment, this is about 20 to 32%, and we do not use too large paste content. This you will recall that we said that aggregate constitute about 70% of the concrete system in the beginning when we defined concrete, right. So, that is the role of paste, right. Now, let us look at the role of aggregate. Well, aggregates are inert material, they should not react, they do not react with the take part in hydration process and should remain inert even in the future life, otherwise durability could be a problem. So, they are generally inert material, bulk of the material that forms a concrete and provides strength and stability to the concrete system, as we have mentioned earlier. So, they are inert material and they form generally skeleton of the concrete, if I may say so. And for economy, normal concrete one would like to minimize the volume of paste, that is what I have mentioned, and maximize the aggregate volume fraction. So, that is what it is, one would like to do there. Now, interstitial void space in the dry aggregate system is altered when paste is introduced. We said that because this happens is because of particle interference, or if you introduce a new material into the pore space or interstitial pore space of larger size particle, a point comes when they start pushing the larger size particle itself, it is called interference, particle interference. So, paste also causes some sort of interference, and therefore, this void system space in the dry aggregate system is altered, it is actually increased, and then paste required to ensure dispersion of aggregates is higher than the interstitial porosity of the aggregate, that is what I have mentioned, right. So, what I need a paste which should be more than that existing into the aggregate system alone when packed. So, if that means minimum level is the void content of the paste itself, aggregate itself, aggregate system itself, it will be more than that. So, if I reduce down the void content of the aggregate themselves, then the paste content I can reduce. So, to reduce the, because we for reasons of economy would like to keep it as low as possible with adequate workability. We would like to keep it as low as possible for adequate workability, just the maximum level is that required for workability. So, but I would like to keep it as low as possible for a given workability. So, I must have a good packing of the aggregate system such that its voids are minimal. So, that aggregate porosity, interstitial porosity is minimal, and that is what we would like to do. That is what we would like to do. So, aggregate porosity should be minimal. So, aggregate should pack very well, aggregate should pack very well, and this can be expressed in terms of what is known as packing density. Packing density, this can be expressed in terms of what is known as packing density. Packing density is nothing but it is the volume of the solids in unit bulk volume. So, total volume, if it is in unit total volume, what is the volume of the solids, that is called packing density, and it is nothing but 1 minus P, where P is the porosity, P is the porosity, interstitial porosity of the aggregate. So, 1 minus interstitial porosity is the packing density. So, we would like to maximize the packing density so that P is minimized, and if P is minimized I will need P plus something amount of paste. So, if I have minimized, if I reduce the P, therefore, paste requirement also will reduce for a given workability. So, role of aggregate is therefore to provide a skeleton system which get dispersed into the matrix, but should have a low porosity, should have a high packing density. Now, how do we achieve that? If we look at packing density of single sized particle, if we look at packing density of single sized particle, if we look at packing density of single sized particle, right, say just one unit size, say spheres, then they would pack single sized particle, they would simply pack to a relatively low packing density, even if it is spheres, they will relatively low packing density, and it depends upon its packing arrangement, For example, this is a simple cubic arrangement, it will have a characteristics porosity of about 48%, or in other words the packing density of about 0.52, we shall see that. So, simple arrangement, but supposing I have better, let us say body centered cubic arrangement or face centered cubic arrangement, then I have better packing density. So, but you see this cannot be, there is a limitation, I can't go beyond. With single sized particle, the porosity, which is nothing but the volume of voids present, volume of voids present here, divided by the total bulk volume, that is the ratio actually, and that ratio is for a given single sized particle is relatively quite high, the porosity is quite high, you can't reduce it. Whatever may be the size of this particle, irrespective of the size of the particle, porosity remains same, because you can make size finer or coarser, porosity will remain same, because relative volume, relative total volume, relative volume of the pores divided by the relative total volume I am interested in. So, relative volume of this volume divided by this volume. Similarly, in another case, if I have smaller particles, in that case the pores are here, this relative volume, or may I use another color, relative volume, relative volume of pore to the total volume or porosity, they would remain same irrespective of the size of the particle. So, that is important. So, if you have single sized particle, you will have porosity similar irrespective of the size of the particle, it will depend only on packing, right. As I was mentioning, the packing density of simple cubic, body centered cubic and face centered cubic arrangements are 0.52, 0.68 or 0.74. One can theoretically calculate this. If you have looked into crystal structure in your school days, arrangement of crystals, this is also there in those cases. So, you can see that if I have a simple cubic arrangement, irrespective of the particle size, irrespective of the size of the particle, the packing density is 0.52. Irrespective of the particle size, it is 0.68 for body centered cubic, and for face centered cubic is 0.74. So, single particle size will always give you this. So, it is not single particle size is definitely not a very efficient thing to do, right. Actual packing density of course, in case of sphere of single size lies somewhere between 0.5 to 0.64 and 0.74, 0.5 to 0.68 so, okay, right, depending upon what is the arrangement. So, you can't really improve it very much, because 0.74 is a specific type of arrangement which you never get. You can get, you get actually theoretically that is possible, but actually that is the maximum, theoretical maximum, but you get it much less packing density with single size, right. Okay. But supposing I add another size to the same single sized particulate system, this will improve the packing density, because the finer size, say original was larger size, now I put a finer size, the finer size will go into the interstitial pores of the original quartz size and resulting in reduction in the void space, right. So, if we want to get higher packing density, then we should actually use aggregate of different sizes, So, if we want to get higher packing density, we should use aggregates of different particle size, and that is what we actually do in practice. The proportions of different size fractions shall be appropriate, because you just can't add anything to anything, any proportion, and you will get improve it. No, there is in certain rules you must do it according to certain rules, and that is how you can maximize the packing density, right. Now, we will look into the case of a binary mixture, and we shall see how this packing density increases. We will see the binary mixture and we will see how this increases, right. Okay. So, we will go to the binary mixture and we will see how this increases, right. So, okay. So, this degree of improvement also depends upon the size ratio. So, we will go to the binary mixture and see how this packing density increases with another size material, and degree of improvement of course depends upon the size ratio. We shall see that next. Okay, consider this case. Supposing I have got a single sized particle as shown here, single sized particle, it is all same size spheres, let me say nearly rounded all aggregate. Now, I add to this fine particles. So, where they will go? Just little bit, very small amount, then it will go into the interstitial pore space. This red ones are the fine particle that I have added into the system. So, they will go into the pore space, interstitial pore space of the large particulate system. If I go on adding further, then of course, they will go on filling and reducing down the voids, because they are going into the interstitial pore spaces. But a time will come that the original packing of the large size aggregate will be disturbed. A time will come when original packing of those large size particles would be disturbed, and that is time they would get separated further, because these fine particles have come and they are trying to occupy the space within that. So, this is called particle interference. So, the rate at which the voids were reducing will now diminish. Let me repeat, first of all you have got all large size particle, you put very small amount of fine size particle, it will go into the interstitial space, pore space of the large particle without disturbing the large size particle. So, voids will reduce. Now, next what will happen? Next actually as you go on increasing it further, it will, the fine particles, they will tend to go into the pore space between the larger particle, but they will try to push this larger particle apart. So, this is called particle interference. So, rate at which voids should be reducing would get now reduced. Initially it will reduce, the voids will reduce at a higher rate with increase in the fine particle, but if you go on further adding finer and finer particle, you will not get reduction of voids at the same rate. But when you have add too much quantity of these fine particles, then fine particles will start dominating, and actually the pores, because if they are more than this void space available, then they will be separately as a separate material. So, void space within the fine particles will now add to the voids. So, in other words, if you look at packing density will initially decrease but its rate of decrease, rate of decrement would reduce. There will be a maximum and then it will start increasing. We can see that, let us see, we can see that how it occurs. See, supposing I have got now from the reverse side, when too much of fines are there, I have a situation like this, too much of fine, and I add too much of fine, it was full, and I have just add this material here, remove some of this and put a large size particle as this. So, in such situation, when too much of fine is there, little bit large size particle, one just for large size particle I have added, this volume is now pure solid volume. So, it will reduce down the voids. In other words, packing density would increase. So, when I started earlier from coarse side particle, added fine particle. Supposing I have large fine particle from the other side and I just remove some amount of fine particle, put a coarse particle, the void will again reduce, packing density will increase. Go on doing this, this will occur in the same manner, but after some time the packing or characteristics of fine particles will be disturbed by the large particle themselves. The result is something like this, the result is something like this, the result is something like this. The packing density versus fraction curves would be something of this kind, packing density versus fraction curves would be something of this kind. Supposing A and B, this is larger one is, let us say, is A, larger one say this is A and this red ones are B. So, A I increase, go on, B was 100% here, I go on increasing A. So the packing density will initially increase, but the rate of increase is not linear, it goes on reducing down, a peak is reached and it follows like this. Similarly, if I start from this side, I have got all large particle, then the small particle I go on adding a little bit, packing density will increase, there will be maxima and there will be reduction. So, what we observe from this is packing density increases linearly with addition of second size, but increases less than proportionally thereafter due to particle interference, and thereafter it increases. So, there is a maximum point of packing density and at particular proportion you will get maximum, and by adding two particle size you can increase the packing density. If we go back again to the earlier one, again, we will see that packing density of B was here, we will see that packing density of B was here actually, packing density of B was here, packing density of B was here and packing density of A was here. So, as we have combined two materials, the packing density has actually improved, it is much higher than both of them, it is much higher than both of them. So, by adding two different particle size, we can actually improve the packing density. If we repeat this for many particle sizes, the packing density we can maximize. So, we can increase the packing density from binary mixture to trinary mixture, packing density will still increase, and if you have a multinary mixture, then the packing density will increase in a significant manner, right. So, each subsequent addition of sizes actually will increase the packing density. So, that is the idea. So, therefore, we should have large, that is why we use several sizes of aggregates in concrete to reduce down the packing density, so that our paste content required for a given workability is less. We can identify the optimal fraction, as we have seen by some simple equations one can identify, but overall if you have a multinary system, it becomes a complex thing, requires certain experimental factors, experimental determination of certain factors, right. We can identify, but we do not do that actually, because these theories were not really clearly developed. Of late only there are certain models available on packing density. So, what we do is we use what is known as practical grading, right. Okay. So, practical gradings we use actually instead of using. So, this we said that we can do it, but theoretically we do not do it to ensure dispersion and to take care of particle interference, etc. Okay, this is another issue. The mortar use should be little more than the voids corresponding to the coarser aggregate, right, maximum density of coarser aggregate. Paste should be more than the void space in the all total aggregate, and the paste and sand that makes the mortar should be slightly more. In mortar actually the coarser aggregate get dispersed, therefore, mortar should be slightly more than that of the voids in the coarser aggregate system, right. Okay. So, in any case, as I said, in normal concrete what we do is we use practical gradings, these are proposed, and practical gradings which are proposed in codes, and for basically we can't model it for packing density, etc. It is there are a lot of lot of complexity involved, varies from place to place. So at the moment the practice is to use practical grading curves for normal grade of concrete, although there are mixed design based on packing density as well. Now they are available in literature, but common practice is to ensure that your aggregate falls into a right kind of particle size distribution, because that would give you good kind of packing. So the ranges of particle size distribution that is proposed, and this we call aggregate grading. So range of size fraction of overall aggregate system, these are proposed. For example, IS 383 is the code, Indian standard code is IS 383, and there this is for all in aggregate. When you have sand and aggregate combined, this is a kind of grading suggested. Let us say for grading suggested for 40 mm maximum sized aggregate, MSS stand for maximum size aggregate, 20 mm maximum size aggregate. So it should pass through 80 mm sieve 100%, 40 mm, etc., etc. So it tells you that it must by sieve analysis, actually we do it. We do it by sieve analysis. We have nominal sieve size, square sieve size, and 100% should pass through 80 millimeter, 80 mm square sieves. So and because they are not the spherical particles, they are any can be irregular, crust, etc., etc. So this through this sieve analysis results, gradings are confirmed, right, and this is the suggested grading, that should be proposed grading one should follow in case of all in aggregate as per IS code. Similar grading curves are available for coarse aggregate alone or sands, these are given in the same code, it is given. I just picked up one to show you the as an example, show you the grading, but details are all available in the same code, right. Now for fine aggregates, the code defines 4 grading zones, finest is zone 4 and zone 1 is the coarsest. So it defines actually 4 zones, zone 4 and zone 1, 1, 2, 3, 4, 4 is the finest with maximum fine particle and 1 is the coarsest. So fine aggregates, that is usually sand or crushed sand or whatever it is, or river sand or land quarried sand, this gradings are defined. The one table I showed corresponds to combined aggregate, but you can have separate one also. In some places you might come across what is known as fineness modulus of sand, because fineness modulus also defines like the zone defines the sizes of the sand, fineness modulus also defines the average size of the sand, average size of the fine aggregate in terms of the sieve number, average sieve number, right. So that's how it defines. Just let's look into the fineness modulus. Fineness modulus of ith size starting from 75 micron size is given as 3.73, that is an expression, very simple expression, and if you put di equals to 75 micron here, if you put di equals to 75 micron here, d1, least you will find this value is equals to 0. If you put 150 micron, because our sieve quotient is 2, 75 then 150 micron is the quotient, this is called quotient, multiply by 2 you get the next sieve size 150, multiply by another 2, 300, 600, 120, 1.25, 1.18 millimeter, that is, and 2.36, so nearly about 2 and so on, because they got changed from the British unit to the SI or what you call MKS or CGS unit, and therefore there are slight differences, but usually nearly about 2. So sieve quotient is 2 and log 2 is 0.3010 multiplied by 0.322 will give you 1. So D as this is 75, this is equals to 0. If it is 150, this will be equals to 1. If it is 250 300, this will be equals to 2 and so on. So as the sieve size increases, nominal sieve sizes increases, the fineness modulus increases by 1, 2, 3, etc. For example, for 75 micron fineness modulus is 0, 150 micron fineness modulus is 1, and for 300 micron it will be 2, for 600 micron it will be 3, etc., etc. So, in a way fineness modulus for individual sieve size, it corresponds to the sieve number starting from the bottommost sieve, right, which is 0. FM for combined aggregate, that is for sand, which has got all, or sand, or even for total aggregate you can use for any combined aggregate. This is given as a weighted average size. For example, it is given as P1, 2 P2, 3 P2, P3, etc., etc., where P1 and P1, P2, P3, etc., these ones are the mass fraction of particles in 150, 300, 600 micron sizes. So, P1 means the particle fraction in 150 micron passing to 300 retained in 150, I mean passing to 100, passing to 300, and similarly P2 is passing through 600 retained in 300, etc., etc., and if you sum this up, this will give you P1, 2 P2, 3 P2, etc., etc., that will give you the overall fineness modulus of the aggregate system. Well, by algebra one can show that fineness modulus, same thing, can be calculated as cumulative percentage retained, sum of cumulative percentage retained in each sieve divided by 100. You know, if you cumulate total sum, find out total sum of cumulative percentage retained in each sieve. So, you know the cumulative percentage retained in number 1 sieve, number 2 sieve from the top, largest size, the next sieve the cumulative percentage retained will be that retained in the previous sieve and this sieve, and so on. So, if you sum all of them up and divide by 100, you get FM, because this will algebraically be same to this. So, this is a measure of average size in terms of average sieve number, right. So, that is what is a fineness modulus. Sometimes this is used to denote the fineness of the aggregate, like zone 1, zone 2, zone 3, zone 4. Okay. So, we have seen that grading of aggregate is important, because if you have different sizes and the right combination, then you can reduce down the packing density. So, and we do control it through grading. Next aspects about the next aspect about the aggregate, role of aggregate is the size of aggregate. Lowest size of fine aggregate is 75 micron. So, least size is 75 micron, I do not have anything lower than that, then I will go to cement or cementitious sizes. So, 75 micron is the lowest size of aggregate. So, if I want to increase the aggregate packing density, I will have nothing lower, but if I know that if I make the aggregate from binary to trinary, trinary to quaternary, etc., etc., and increase the number of sizes, then packing density improves. So, if I increase the maximum size of aggregates, on the other higher side I am now increasing one more size, therefore, packing density will increase. So, maximum size of aggregate if I increase, packing density will increase. So, nominal maximum size of aggregate implies that increasing number of size, sieve size, number of size from, let us say, from 20 to 40 millimeter means addition of one more size. Therefore, what will happen? This will ensure that my packing density has improved. So, increasing maximum size ensures that I increase my packing density, So, overall voids in the aggregate would thus reduce by increasing MSA, the paste required would be less, that is the idea, the paste required would be less. So, that is the role of MSA. So, two things we have seen so far. One, the grading of aggregate, that is the proportions of various size fraction, and they are important. Also, maximum size of aggregate, that is number of size fraction, that is important. So, maximum size of aggregate actually includes the number of size fractions. Aggregate shape is the next issue. This must be understood very well, because there can be a little bit of confusion sometime. Spherical particles packs to higher packing density compared to irregular shaped particles. This is important. Irregular shaped particles do not pack to good density. Spheres should pack to good packing density, higher packing density. If you have all sorts of irregular, they will leave a lot of voids within, in the interstitial voids within them. Natural aggregates are of course not spheres definitely, but they can be classified as rounded, rounded gravel. Natural gravels will be rounded. If you get it from river bed, they will be all rounded because of abrasion that has gone in, natural abrasion that it would have gone in. So, that would be rounded, because through abrasion. So, natural stones, gravels, if you collect them, they will be rounded. So, rounded aggregates are natural aggregate. Sand, similarly river sand would be grounded, even land quarried sand would be rounded sort of. So, natural ones will be rounded, but if you have crushed, they are unlikely to be rounded, because they will crushed means they have failed in the failure plane, the weakest link, and the crushed ones are not rounded, right. There can be irregular shapes in between somewhere. So, basically we will classify generally for our purpose rounded and crushed later on sometime, but it could be rounded, irregular or crushed. So, one can define them as rounded, irregular or crushed, right. One of the ways, there are several ways of trying to define the, people have tried to define the shapes in several ways, various indexes have been used, but one of the ways that I would like to introduce here is in terms of what is called angularity factor, generally given by Loudon somewhere in 1950s. Now, this he defined as the ratio of specific surface of size group to that of spheres having nominal volume diameter, means the sieve opening. Let me repeat, first you find out, you do sieve analysis, and by permeability test you measure the specific surface of that particular size group. Now, you know the sieve size. So, you find out the specific surface, that is centimeter square per gram, or equivalent unit, inch square per pound or whatever it is, and also from that you find out what is the equivalent diameter. Divide this by the nominal sieve diameter. Now, this is a measure of the angularity, this is the measure of the angularity. Higher this value, it means your surface area is large compared to the volume. For spheres, this is equals to 1, because surface area is to volume diameter, they will give you same identical. Now, here you calculate out the surface area and then try to find out the diameter of equivalent sphere. This diameter will tend to be large, because you will have large surface area, surface area per unit volume, and then try to find out the equivalent diameter. So, for irregular shapes, surface area is more, therefore, corresponding diameter will be more. So, angularity factor is defined in terms of the specific surface of the actual aggregate divided by the nominal sieve size, and that is higher value means it is angular, higher value means it is angular, higher value means it is less spherical. So, that is what one would say. So, for example, you can see the values are 1.1, 1.4 and 1.7 for for 1.1, 1.4 and 1.7 for rounded, irregular and crushed aggregate respectively. It is from measurement at some sizes, there could be slight difference, but it should be understood that for rounded aggregate this value is less, for crushed this value is much higher, the angularity factor is much higher. So, that is the idea, and if we now look at the void content of the aggregate, people have measured this void content with this angularity factor, and they have observed that this we are say linear relationship, this we are say linear relationship. So, this side if I plot void content, if I plot void content along this side, say 0.3 to 0.7, angularity factor increasing along this direction. So, for 1 which is means perfectly sphere, and some data are here. So, you will see that as my void content angularity factor increases, void content increases. So, rounded aggregate packs better, crushed aggregate will pack to lower packing density. Therefore, you need possibly more paste content, rounded aggregates requires less paste. So, rounded aggregates will require less paste, whereas crushed aggregate will require more paste. In other words, workability associated with the rounded aggregate would be better. It would require possibly less water in concrete, as we shall see sometime later on in the context of mixed design. So, aggregate shape is an important issue. So, 3 aspects we have seen. One, the grading, the fractions of different sizes. Second issue is the maximum size of aggregate, that is the number of sizes that is involved. So, that is MSA, and third we are seeing the shape. So, these 3 are the major factors, and they govern the paste content, and therefore, they govern that is the role of their in workability or consistency of concrete. Higher more number of sizes and higher MSA, right kind of grading, proportions of each size is proper, and rounded shape will give you better workability. Right. So, we can now look into how do we change concrete workability. This so far we have talked about only normal strength concrete, and we have not talked about concrete with what is known as admixtures, special additives which you can add to improve the workability, etc., etc. So, normal concrete, the 4 ingredients concrete, that is the cement, the water, a fine aggregate fraction and the coarse aggregate fraction. So, with this concrete, if we have seen what is the role of the paste, water and water cement ratio in the paste, and then we have looked into the role of various aggregates, right. This is so we have looked into the role of the component. We have not looked into anything where by adding some additives we can improve the workability, etc., etc. So, let us look at how do you change the workability if I do not have any admixtures, right. Okay. Plastic deformations in fresh concrete is possible only when there is enough paste. This must be understood. By this time it must be clear that there must be enough paste in the concrete, and the paste itself must be consistent, at least must have enough water, that is initial basic water. You can have higher water, that is fine, right. So, this basic water, that is corresponding to the normal consistency, nearly about same, this has been observed. So, this this should be there. Now, normal, that would give you a normal consistent paste, and normal consistent concrete, normal consistent concrete has a slump of 20 to 50 millimeter. So, normal consistent concrete will have a slump of which has sufficient amount of paste into it, and paste itself is sufficiently consistent. Paste itself is sufficiently consistent, that sort of a concrete will have 20 to 50 millimeter slump, 20 to 50 millimeter slump, right. Let me just point out here, in the context of concrete, we shall see in terms of when we do mixed design, that in mixed design process we initially determine the water to cement ratio from strength criteria. When we discuss further about the strength, we will see that strength is mainly governed by water to cement ratio. So, we fix the water to cement ratio from strength criteria, then from workability criteria fix the water content. The idea is very simple. For given water to cement ratio, if I increase the water content, I am actually increasing the paste content by increasing the water as well as by increasing the cement, because water to cement ratio has to be maintained constant, that I can't change. If I increase simply water, my paste will increase, but strength may reduce. So, I keep the water to cement ratio constant, and water to cement ratio constant, and then increase the water. So, quite often we understand in mixed design that water content governs the workability of concrete, but that is for a constant water to cement ratio. The water cement ratio has to be fixed, then water content has got a big role, because you can't increase the cement. Then if you increase the cement, consistency of the cement paste alone, consistency of the cement paste itself will go down. So, if you increase the water, maintain the water cement ratio, both water will increase, cement will increase, and in the process actually your workability will increase, strength will remain same. So, this is important issue, right. So, to change what I should do? I should actually increase the paste. I should actually increase the paste. I should actually increase the paste, right. And I also already mentioned that volume of air filled to water filled void in case of a consistent mix, in case of consistent cement paste is 1:7. I just mentioned again repeatedly, because consistent cement has to be there. To increase the workability, paste content has to be increased for same water cement ratio, as strength has to be maintained same, right, and this can be done by increasing water content, and that is what we do in case of mixed design. That is what we do in case of mixed design. For water cement ratio to be constant, right, by keeping water cement ratio constant, increase the water content, water workability increases as paste content increases, that is what I have mentioned. Therefore, how do we do? What we see is, supposing I increase delta W, increase the water. I said that I can increase my water content say by delta W. I must keep my water to cement ratio constant, otherwise my strength will be disturbed. So, supposing I have added delta W amount of water, my water to cement ratio has to be constant. So, W divided by delta W divided by C plus delta C, this must be equals to W by C. So, C delta C also, there will be an increase in cement content also. So, I must increase my cement content, and because I must increase my cement content, so I must increase my cement content, W plus delta W divided by C plus delta C should be equals to W by C if I have to maintain water cement ratio same. And using this algebra, if I try to calculate out what would be the increase in the paste volume, the formula will give me this. The formula will give me this, because delta C can be replaced in terms of W by C and delta W, and if I just do a little bit of arithmetic, I will see the volume fraction of increase in paste will be given by this 0.32 C divided by W, where 0.32 C is the specific volume of cement, because we know specific gravity of cement is 3.15. So, 1 by 3.15 is this into C by W plus 1 delta W into 10 to the power minus 3. So, if I add a little bit of water, I actually increase the paste content by this much fraction, volume of fractional increase in the paste content is given by this. So, that is what we actually do in practice, right. A simple equation has been proposed, right, for simple equation has been proposed, alright, simple equation has been proposed for increasing the workability, This is called a K factor method, okay, it does not matter, but let me explain this equation. This can be used. Supposing W2 is the slump or any other consistency measure, usually slump, BB, etc., etc. W2 is the water content for the slump of Y2. So, Y2 is the consistency measure, W1, W is the water, corresponding water. So, what W2 is the water content for Y2 slump, W1 is the water content for Y1 slump. Then W2 by W1 is equals to Y2 by Y1 divided by 1 over I, where I is an index depends upon the method of measurement of consistency of concrete, say slump could be one of them, BB, etc., etc. So, I for slump is 10, for BB it is different, compaction factor the equation becomes slightly different, and so on. So, for each one can define, but I have just taken the case of slump. This is a simple equation through which you can find out how much water should be there. Supposing W1 was the water for your Y1, that is slump equals to 50 millimeter. Now, you want to find out the slump for 100 millimeter. So, this is 100, and what should be the water, that you can find out from this formula. I for slump is 10. So, using this kind of relationship, actually one can find out what is the water requirement. Okay, we might discuss this a little bit more in connection with mixed design. So, therefore, we summarize our discussion. What we have discussed so far is the role of paste. What we have discussed so far is the role of paste. We have discussed the role of paste. We have understood the role of paste. We have understood the role of paste. We have understood the role of aggregates and how workability is increased. Okay. So, we have understood the role of paste, role of aggregate, and how workability is increased. Right. This you will use again in context of mixed design. I think that would summarize all our discussion and end our discussion. Thank you for hearing.